What really creates a rogue wave?
The open ocean is chaotic, but it generally follows rules. Until, without warning, a wall of water rises from nowhere, towering over the surrounding sea, and collapses with catastrophic force. In oceanography, this is a rogue wave. It is strictly defined as a transient surface wave with a height more than twice the significant wave height of the surrounding sea. To understand that definition, we have to look at this diagram. This is a standard wave record, tracking surface elevations over time. If we isolate the top 1/3 of the largest waves and calculate their mean height, we get the significant wave height, or SWH. This is the baseline metric for maritime engineering. For over a century, oceanographers applied a statistical model called the Rayleigh distribution to predict extreme waves. Looking at this curve, the probability of a wave reaching twice the SWH drops so sharply that it becomes a statistical ghost, predicted to occur perhaps once every 10,000 years. In 1995, the Dropner oil platform captured the first objective recording of an extreme wave using a downward-pointing laser sensor, moving the study of rogue waves from maritime lore into hard data. This is the exact amplitude graph recorded by the Dropner laser. The sensor tracks a severe but predictable 12-meter sea state. Then, at 1520 UTC, the elevation suddenly spikes into a massive, solitary peak measuring 25.6 meters from trough to crest. The Dropner wave proved that extreme wave events are frequent physical realities. The data forced the scientific community to abandon the century-old Gaussian sea model and search for the actual physics driving these anomalies. With the statistical model broken, physicists had to determine the mechanical pathways that allow water to stack into these forbidden heights. The search revealed two primary domains of extreme fluid dynamics: linear spatiotemporal focusing and nonlinear modulational instability. Proof of this varied fluid dynamics comes from a 2020 recording near Ucluelet, British Columbia. This event showed that extreme amplification happens across wildly different coastal geometries and weather conditions. Anchored off the rugged coast of Vancouver Island, shown here, a buoy recorded a 17.6-meter wave rising out of a mild 6-meter sea state. That is an amplification ratio nearly 3 times the significant wave height. Because these waves occur in highly varied environments, from the open North Sea to the shores of Vancouver Island, oceanographers know there is no single cause. They are the result of several distinct physical mechanisms converging. The first mechanism is linear spatial temporal focusing. This is a physical process where external environmental factors, specifically currents and winds, force standard waves to merge and pile up. We can see this clearly mapped along the southern tip of Africa. Here, the warm Agulhas current runs southwest, driving directly into prevailing westerly winds. Looking at a cross-section of this interaction, the opposing current acts as a hydraulic brake. It causes the oncoming wave train to compress, shortening the horizontal distance between wave crests. This triggers a process called shoaling. Because the wavelengths are compressed by the current, the kinetic energy has nowhere to go but up. The crests merge and pile upward, violently increasing the wave height. This specific mechanism allows oceanographers to predictably map high-risk rogue wave zones around the globe based entirely on prevailing currents. Yet while spatiotemporal focusing perfectly explains rogue waves in high-current coastal zones, it fails to explain how extreme waves form in the open ocean, where these countercurrents do not exist. In the open ocean, we have to look at constructive interference. This occurs in crossing seas, where wave trains from completely different storm systems intersect. To test this, scientists at Oxford and Edinburgh ran laboratory simulations in 2019, observing what happens when waves cross at varying angles. In this 3D simulation, 2 wave trains run parallel at a 0-degree angle. Their combined crest breaks horizontally and plunges downward. At shallow intersection angles, like this 60-degree cross, the wave acts as a plunging breaker. It collapses under its own weight, which effectively limits its maximum height, even with a slight upward lift. The critical anomaly appears when the wave trains intersect at exactly 120 degrees. At this precise angle, the waves collide and violently erupt into a vertical jet that does not immediately break. The 120-degree geometry prevents the crest from plunging. Instead of collapsing, the intersecting waves stack their kinetic energy straight up into an extreme, towering peak. A chaotic sea state with highly variable crossing wave directions actually acts as a structural foundation. It mathematically allows water to stack into transient towers without violating the laws of fluid dynamics. But there is an even more terrifying mechanism. In deep water, a rogue wave can form from a single unidirectional swell, requiring no crossing seas or opposing currents at all. Standard linear wave equations break down completely here. To model this instability, physicists introduce the nonlinear Schrödinger equation. This animation models the initial state of modulational instability. We start with a perfectly uniform sea state rolling across the surface. Then, a subtle physical perturbation occurs. That unstable wave actively drains kinetic energy from the waves immediately in front of and behind it. As the central peak swells, the adjacent waves are reduced to minor ripples. The resulting formation is known as a peregrine soliton, or breather. Because the energy was literally stolen from the adjacent waves, the monster crest is flanked by two deep inverted profiles known as rogue holes. The reality of encountering this structure at sea is lethal. A ship drops instantly into a deep, unexpected trench, pitching its bow down, just as a vertical wall of water crashes directly over the deck. The ocean is a non-linear medium. Under the right conditions, a perfectly normal wave will spontaneously cannibalize its neighbors to become a momentary giant. Translating these fluid dynamics into engineering reveals exactly why rogue waves destroy ships built to standard codes. Look at the schematic. A standard 12-meter wave safely exerts 6 metric tons per square meter of braking force, but a plunging rogue wave creates extreme impulse pressure spikes, Giffel peaks, slamming the hull with dynamic loads exceeding 100 metric tons per square meter. These microsecond dynamic spikes exert enough concentrated force to cause sudden, brittle fracture in mild maritime steel, instantly breaching a ship's watertight integrity. Forensic investigations into lost ships repeatedly point to this specific mode of catastrophic structural failure. Massive, state-of-the-art vessels like the SS Edmund Fitzgerald shown here have been lost suddenly to these anomalous wave interactions. When a Giffel peak impacts a ship's deck hatches or superstructure, the violence is absolute. These components are rarely rated for these dynamic kinetic loads. A rogue wave delivers localized kinetic shockwaves that target the structural limits of maritime vessels, bypassing standard engineering tolerances. For decades, there was lingering skepticism regarding how often these mathematical and physical anomalies actually align in the real world. To measure this, the European Space Agency launched the MaxWave project, using satellite radar to scan the global oceans and hunt for rogue signatures. This map visualizes a startling reality. In just a 3-week scanning period, the satellites recorded over 10 individual giant waves exceeding 25 meters in height. Whether driven by the Agulhas currents, 120-degree crossing seas, or nonlinear modulational instability, rogue waves are a daily feature of Earth's oceans. The Dropner wave recording corrected a major statistical error and established the nonlinear, unpredictable reality of ocean fluid dynamics.